The last colligative property that I'm going to cover is freezing point depression. So in the opposite fashion of boiling point, where we saw adding a solute increase the boiling point, when we add a solute, we will actually see the freezing point of that solvent go down. So if this is water, we know the freezing point is 0 degrees Celsius. When we add a solute, the freezing point will be lower than 0 degrees Celsius. How do we calculate how much lower, I should say, the freezing point is? So the change in temperature freezing, this will be very similar to the boiling point elevation formula. Remember, this will be lower than our original, is going to be equal to Kf, which is our freezing point depression constant. And again, this will be from a table. You would not memorize this for every liquid, times colligative molality. This is colligative molality. This is M times I, and this will be Kelvin times kilogram per mole. This will be moles of solute over kilograms of solvent. That will cancel, that will cancel. We'll be left with Kelvin, which is what we want. We want a change in freezing temperature. So the explanation for why the freezing point goes down is a little bit trickier than the boiling point elevation explanation. So when we picture water in the liquid form, trying to freeze and condense into this ice block, what we can think of is as the solute is added to this liquid, it makes it more difficult to build that solid block because those solute particles are going to disrupt those water molecules' ability to form those nice block structures of ice. The solute will get in the way and the water will have to overcome that and freeze at even lower of a temperature. So we will have to lower the temperature even further for those water molecules to really freeze and make those solid blocks of ice. So that is the explanation. And this is how you would solve for that change in temperature freezing using that freezing point depression constant and the colligative molality.